Welcome to homework.
So first, set the free body diagram from figure 12.29 and modify it to indicate the changes in the roadway mass distribution. You might also need to draw the free body diagrams for point A and B. So I have drawn them separately over here. Now, that example, if the roadway mass is 1.4 times 10 to the power 6 kg. So this was the roadway mass in that example. Then for one truss, we should use M to be equal to 7 times 10 to the power 5 kg. Now let's write the conditions for equilibrium for the entire truss by considering vertical forces and torques about the point A. So about this point. And here I am taking clockwise torques to be positive. So first let's write the torque equation, and this gives half mg times this distance AC, which is given to be 32 meter, plus 1/4 of mg, which is this force over here, times the distance AE, and that is 32 plus 32, since both are equal, AC and CE segments are equal. So we have 32 plus 32, which gives 64 meter. Then we have a counterclockwise torque due to F2. So we take F2 times the same distance, and that gives 0. 1/4 of mg, the force over here, and F1 don't give any torques because they pass through point A. So, and we are calculating the torques about point A. So they don't give any torque about that point. So if you simplify this, you get F2 to be equal to half of mg. Now let's write Newton's law for the vertical direction. So we have F1 going up, F2 going down, and then three of these. So let me write that together, and all these forces go down, and that is equal to 0. So this gives F1 plus F2 minus mg. So these factors sum up to mg. And from here you can find F1, which comes out to be mg minus F2. So you plug this value of mg over here and you get F1 to be equal to half of mg. So now we have another force. Now note that the problem is still symmetric about this vertical line through C. So let me draw that line. So the problem is symmetric about this point, about this line. So the forces at the ends each bear half of the weight of that side of the structure. So it will be clear after a while when I start working on those parts. Now the second thing we need to do is analyze the force, analyze all the forces on the pin at point A. So I have drawn the free body diagram over here. So if we analyze that and write Newton's second law for vertical and horizontal direction and solve them after. So for the vertical direction, we have half mg minus 1/4 of mg minus FAB sine 60 degree to be equal to 0. And for horizontal direction, we have FAC minus FAB cos 60 degree to be equal to 0. So basically here I'm taking the components of FAB in horizontal and vertical direction. So as you see, this angle is 60 degree. So FAB cos 60 degree will be the horizontal component towards right, and FAB sin 60 degree will the vertical component towards up. And here I am taking the left side to be positive and down to be, sorry, okay. Oh, I guess yeah, okay. So FAB cos 60 degree is towards left for the pin A, for the pin at point A. So FAB cos 60 degree is towards left. So therefore there is a negative sign here, and FAB sine 60 degree is downwards. So here there is a negative sign. And we are going with the usual assumption, that is positive x-axis is towards right and positive y-axis is upwards. Now solving this, we get FAC to be equal to FAB 60 degree, cos 60 degree. Now if you solve this equation, let me just move this over here. Now if we solve the first equation, we will find FAB to be equal to mg over 2 times root over of 3. Then you can find FAC by plugging this value of FAB over here. So doing that, you get FAC to be equal to mg over 4 root 3. Then to find FBC and FDB, we will analyze the forces at the for the pin at point B. And we go with the same method. So we write Newton's second law at point B for the horizontal and vertical direction. So for the vertical direction, we get FAB sine 60 degree minus FBC sine 60 degree to be equal to 0. So this gives FBC to be equal to FAB, and we already calculated FAB over here. So just plug that value and you get FBC, the magnitude of FBC. Now for FH, for the horizontal forces, we have FAB cos 60 degree plus FBC cos 60 degree minus FTB. And this gives FTB to be equal to FAB plus FBC times cos 60 degree. And using the values of FAB and FBC, which basically are equal and equal to mg over 2 root 3, so we plug this value over here and we get FDB to be equal to twice of mg over 2 root 3 times cos 60, which is 1 over 2, and therefore this value is mg over 2 root 3. Now we have 4 of these forces. So basically we have all the forces for one side of the truss. So we have all these forces of the left side of the truss, and by symmetry of the geometry we can determine other forces. So FDE, which is here, so FDE will be equal to FAB. So this will be equal to mg over 2 root 3, and FDC will be equal to FABC, and this will be equal to mg2 root 3, and FCE will be equal to FAC, this will be equal to mg over 4 root 3 as we calculated. Now, depending on the direction of these forces and which of these segments are getting stretched and getting compressed, so basically the direction of the forces that we found, FAC, FAB, and FBC, and FDB, you can find which of these are in tension or compression. So FDE and DB are getting compressed, as you can see over here. So they are in compression. This is, so these are in compression, stands for C. This is in tension, and CEAC are in tension again. Now, if you compare this solution to example 11, you'll find that each force is reduced by a factor of 2.